All right, we should be good. Okay, so, well, first off, you're probably wondering why I'm not Sam. Well, that's because I'm not Sam. Wow, I know. Brilliant, right? Okay, anyway. So, in the last video, Sam talked about something called command based programming. So, that's when you basically have your own subsystems and then you have different commands for each subsystem, and each of the commands calls a subsystem, and each subsystem will do a particular thing depending on your command. Now, today we're going to evolve a little bit based off of that, and we're going to start programming some autonomous routines. Now, these are going to be fairly basic in comparison to what we're going to talk about in the future, but it's a very good, segue into autonomous, and we're just feeding off of the command-based knowledge that you already know. So if I head over to VS Code, you guys can see my lovely theme over here. So last time, I'm just going to delete this real quick. Alrighty, so last time when we worked with Sam, you guys made two different subsystems, a drive subsystem and an intake subsystem. And we worked with these and, all said and done. So we had a drive subsystem where we declared two different sides, a left drive primary and a right drive primary, and each one had a follower. And then in intake, we just had one motor that we were controlling with a percent output based on a speed that we passed through. And then in our command, we had a default drive command, and that's getting your controller access, and based on controller access, it's sending a percent output. And then your run intake command is just executing depending on whenever it's pressed. And so in this case, we're just running it for 70% speed. So what you'll find is that a lot of the autonomous coding that we do sort of branches off these different commands. So, this run intake command and this default drive command, these are foundational commands that we're going to use to create our own autonomous commands. So let's just sort of walk through how, a typical autonomous, routine works. Usually we have a lot of things going on at once, but the general gist of our commands is that we want everything to be pre-programmed, and we want everything to be pre-programmed exactly to what we want. So obviously something like, creating a drive command based on a controller access is not going to work because, where's your controller access? And things like run intake command, well, this is similar. We can optimize this a little bit just to make sure it works nicely with our autonomous, and also just to make our own auton commands. That way we don't interfere with the telyup commands. Because, sometimes you might have it when you run code, maybe the auton command works and the telyup command doesn't. So you want to keep them separate. So to get started with the autonomous part, I want to first slightly edit our drive subsystem a little bit. And in the auto drive command that we're going to write, so that's going to be the command that lets the robot drive on its own. We're actually going to command it in a little bit of a different way than what Sam told us. And what we're going to do is, and what I want to introduce you guys to, is something called the differential drive object. Now, differential drive, well, as you're probably familiar with, there's two different types of drivetrains, right? The first type is, your standard tank drive, and the other one is a swerve drive. And those are the ones we typically use in FRC. Now, differential drive is a special class or a special object type that's made by WPILib that allows us to very easily control a standard tank drive. So our robot, as you know, has got a standard tank drive, right? So we've got 3 motors on the left side, 3 motors on the right side. And effectively what the differential drive object allows us to do is very easily command those motors to do exactly what we want them to. So in order to set up this drivetrain to use the differential drive object, we're first going to create it. So we're going to make it public for now. And final just means, hey, this is the object. We can't change it. It's going to be of type differential drive. And for now, we'll just call it ArcadeDrive. That's usually the convention that we use. All right, so we've got this set up here. Now we're just going to instantiate it or give it an actual, an actual value to work with inside our constructor here. So I'm going to say KDrive equals new differential drive. Now the differential drive takes in two different parameters, and these two parameters are motor groups. Now if you remember, our two motor groups are left drive primary and right drive primary. So that's exactly what I'm going to pass through. Left drive primary and then right drive primary. Feel free to pause the video if you need to finish up typing or anything. No big deal there. All right, so that pretty much sets up our differential drive there. Just two quick lines of code, just saying, hey, we want to be able to use differential drive object in order to command our robot. Now let's just go. Let's just quickly go through this default drive command here because this is actually fine as it is. But for autonomous, things get a little bit easier in that when we command things autonomously, we control the motor output, and so that makes it a little bit easier for us to work with. So we don't necessarily need to base our commands solely off of something like controller input. Since we command the drive speed and we command how much we want it to move, that gives us a lot more flexibility in terms of what we can do. So let's just quickly go through this. So in this command here, we're taking in a few different things. We've got the left and right speed, I assume, here. And so I'm not going to talk about slew rate limiters. I'm sure Sam went into detail on that. But we're initializing them to 0. And then here we're initializing the left speed to whatever the left y-axis is from the joystick, and the same thing for the right from the right y-axis. And so while this is a standard way to control a tank drivetrain, and actually, let me, if I can show you the way that works. So the way this command works right now is you've got two sets of wheels like this. And effectively what this command is doing is it's individually controlling each side of the drivetrain. So we're individually controlling this left side here, and we're individually controlling this right side here. What differential drive allows us to do is to use something called ArcadeDrive. Now, this is a slightly different way of controlling your drivetrain. So in a tank drive, what you're essentially doing is you're commanding each side, right? So let's say I could command this left side to be at 50% speed, and I could command this to be at 25% speed. And since the left side's overpowering the right side, the robot's going to turn something like that way, right? Now, ArcadeDrive is actually a little bit more, I'd say, easier to control in terms of linear movement forward and backward. So here's how that works. So let me just get rid of this here. So let's just Control Z. All right, so back to our drivetrain here. So what ArcadeDrive allows us to do is, and if I have my controller here, let's just imagine that these are the two joysticks on your Xbox controller, right? I'll just like sort of draw that here. Now, previously, if you worked with tank drive, your standard tank drive controls, you'd only have two options. You could either move this stick forward and backward, or this stick forward and backward. And that's pretty much it. That's how we command it. Now, ArcadeDrive is a little bit different. In this case, your left stick here, so this stick right here, controls the entire robot moving forward. So it controls both sides of the robot moving forward and both sides of the robot moving backward. So with this one joystick here, if I move it forward in the Y direction, the entire robot will move forward. And if I move it backward in the Y direction, the entire robot will move backward. So both sides of the drivetrain, this left side here and this right side here, are moving at the exact same rate, and that's linear forward motion, linear backward motion. Now, this right stick over here at the bottom, you move in the X direction. So you can either move it right or you move it left. And now moving it right, what it does is it effectively spins the robot in place. So what you can do is say, let's say I had this initial configuration. If I move my right stick to the right, now I could have my robot face like this. If you imagine these are like the track width of the robot per se. If I moved it to the right, maybe my robot curves like that. Maybe it curves like that. If I moved it to the left, I could get my robot to curve like that. I could get it to curve like that. So effectively, it's sort of just spinning in place. And obviously, if you give it, and you have the option to spin in place, but also if you move forward and continue to turn, it's almost like you're driving, right? Like you're moving forward and you're turning your steering wheel. And if you imagine this to be the steering wheel, I think that's a good way to look at it. So this is sort of your acceleration pedal, your gas pedal. So moving it forward and backward. And this here is basically your steering wheel. So moving it left and right. And I think that's a good way to visualize that. So that's ArcadeDrive. It's a little bit different in terms of controlling. So we're not independently controlling each side in terms of just raw percent out or percent output for each side, just moving only forward and backward. But rather, WPIlib, it lets us, or it gives us rather, a way of controlling our robot by allowing it to spin or pivot in place. And that's basically what this right joystick does. Okay, so now that we've gone over that, let's make our auto drive command. So I'm not going to save this. Let's create a new command. Oop. Let's try that again. Cool. Command, new. Let's give this, let's call it auto drive. Cool. Now you've got our command. So the first thing we're going to do, like in this command, is declare our drive system subsystem. So let's do that real quick. So we've got, all right, I don't know why I clicked out. We've got our private drive subsystem, and we'll call it drive underscore subsystem. Now the next thing I want to do is just declare two quick doubles, or decimal values. We're going to call it vertical speed and horizontal speed. And I'll explain why we need those in a second. So now in auto drive, in this constructor, I'm going to pass in, drive subsystem. We'll just call it drive here, just to make it easier on us. We'll have a double V for vertical speed and double H for horizontal speed. And then within this, we're first going to add our requirements for drive subsystem. Or in this case, drive, because that's what we're passing in the constructor. And then I'm going to set vertical speed equal to V and horizontal speed equal to H. Cool, got that done. And I almost forgot, drive subsystem is equal to drive. Cool. So that's just, setting up our drive subsystem, and we've got two extra numbers that don't worry about them now. I'm going to talk about them later. So let's head over to execute. And in order to, actually use a differential drive object to make it easier to drive, to arcade drive, to actually drive, we do drive subsystem .k drive. So we're going to reference that differential drive object that we made earlier. And now this differential drive object has a method called ArcadeDrive. And this is where things get fun. So you can see it accepts something called X speed and Z rotation. Now this is what I was talking about earlier, right? So if we go back to me for a second, this X speed here is referring to forward and backward speeds. So a positive speed value is going to move the entire robot forward. A negative speed value will move the entire robot backward. Now, Z rotation, or in this case, is robot rotation. So it's effectively saying, how fast do you want the robot to spin in place? So spinning in place, meaning something like that. Or you can imagine it in a way, like a good analogy is, how fast do you want to turn the steering wheel on your car, right, while you're moving? So that's a good way of visualizing it there. So in this case, we're just going to pass in vertical speed and horizontal speed. Now, the reason why I call it horizontal speed will actually make sense when we actually write our auton paths. For now, our goal is we won't be working so much with horizontal speed because we want to make sure that we understand the autonomous routines, and then we'll talk more about horizontal speed later on. But for now, let's just keep this in mind, that horizontal speed is something that we can control and allows us to control the rate at which we actually turn the actual robot in the first place. Alrighty. So we obviously need to add our end condition, and it's actually pretty easy. We can just use a KDrive object again and just pass in 0. That's just not going to make the robot move. It's as simple as that. So now that we've got that covered, give me 1 second here. Alrighty. Okay, now that we've got that covered, let's talk a little bit about the intake. So our run intake command right now, what it's doing is it's setting a percent output to the intake. So in this case, something like 70% every time this command is called. Now the auto intake command is actually not that different. The only difference is that depending on our autonomous routine, we might want to do different things with the intake. So in rather than just setting it to zero point 0.7 by default, we're just going to make a new auto intake command. And again, this gives you practice with making commands. So we're just going to make a new one. And rather than just set it at zero point 0.7, I just want to set it to whatever speed I pass in. So whatever speed I pass into this command, I want it to run at that speed. So new command. And actually, why don't you give this a try before you actually watch me do it? So if you want, pause the video right here and see if you can make a very similar auto intake command. And the only difference is that it takes in a speed. It's the only difference. So we're not commanding it at just raw 70%. It needs to take in a speed. So go ahead and give that a try. All right. Okay. Hopefully you gave that a try. So we're going to start by creating our intake subsystem. Let's call it intake. And then we're going to have a private parameter. Oops. Private double speed. Just call it speed. Or call it S. Whatever you want. Whatever tickles your fancy. And then inside our constructor, we're going to pass in the intake. I'll just call it I for now. And then we'll pass in double speed. So first, we must add our requirements. Then we're going to say intake equals I. And then speed equals speed. So there you go. Pass them in. Now we're just going to run our intake and execute. So intake dot set. Let me just make sure that's the right method. Let me just refer back here. Yep, intake dot set. And we're just going to set it for speed. That's it. And then in our end condition, of course, don't forget intake dot set 0. We want to make sure command actually ends. Okay, cool. So those are all the commands we're going to work with for now, just to get a basic, autonomous idea. Now, what we're going to do is just start coding some basic autonomous routines. And the first one that I want to work with is just getting the robot to simply move forward. That's it. Nothing crazy, just move forward. Now, before we even begin, there's an interesting, I don't want to say interesting, but I'll say it's a little bit of a different way we create our autonomous commands. So what I like to do first is just, create a new folder and call it autons, just so it's out of the way of all of it. And then within that folder, we're going to create a command. Let's call it a drive forward auto. Now, rather than extend a normal command base, we're going to extend something called a sequential command group. You might be wondering, all right, well, what is a sequential command group? Now, a sequential command group it's similar to how you design your typical command. The only difference is that all of these methods, they're not really relevant for a sequential command group, or in the case in which we use it in autonomous. So what a sequential command group basically is it allows you to run a certain command for a specific length of time. And if you can imagine here, I'll go back to Paint. Let's just create like sort of a sequential command timeline per se. So let's say we start up here, right? And let's say we want to drive. So that's the first thing we do. What a sequential command group allows us to do is do this for a specified amount of time. So unlike a normal command where you need something like a controller to get it to run the execute method, sequential command group just completely ignores that and just runs it for a specified amount of time, or for as long as you want it to. So let's say in this case we just want to drive and we want to do it for 3 seconds. And then let's say maybe after that we want to run the intake and we want to do that for 1 second. That's exactly what the sequential command group allows us to do. Is we can run these specified commands for a certain amount of time. And the way it works is we just run everything within the constructor. So this constructor that you see here, public drive forward auto, once this constructor is called, that's pretty much it. That's your autonomous routine. That is all. So the way it works is that this constructor right here, I'm just going to get rid of this comment for now, is it takes in the necessary subsystem. So since we're only driving forward, what we're first going to do is just pass in drive subsystem drive underscore subsystem. That's all we're going to take. We're not going to make it anywhere. We're just passing it through the constructor. Now, within the constructor itself, we're going to write add commands, and then we add a series of commands. Now, this is the beauty of sequential command group. Within this add command, I can use my auto drive and auto intake commands and just run them for, however long I want. So, what we're going to do, and by nature, this add commands, because we're extending the sequential command group, all of these commands are running sequentially. Now I'm going to introduce you to a different type of command group later on after this, but for now, just worry about sequential command group and that they run sequentially, meaning that one command is going to run first, and then after that amount of time, it's going to run, the next command is going to run. So for now, we're only running one command. So in this case, we're going to run our auto drive command. And to do that, we're going to type in new auto drive. We're going to pass in our drive subsystem. And remember, it's taking in a vertical speed and a horizontal speed. Now, because we're just moving forward, do we actually need to steer our robot when we move forward? No, right? So our horizontal value is just going to be 0. And let's say we want to move our robot at 50% speed. So we're going to pass in something like 0.5. And there we go. This is all you need to move your robot forward. So let's just take it in for a sec and give this another review. So all we're doing is we're using the sequential command group, and within the constructor, we're adding commands. And these commands will run sequentially, meaning they'll run in order. And now all this is doing is moving forward. Now, you might be wondering, well, there's no timeout. This isn't running for any specified amount of time. So it's just going to move forward forever. And you'd be right in that. So instead, if we wanted to run this for a set amount of time, we can just add dot with timeout and just put in some amount of time. And let's say I wanted to move forward for 5 seconds. Now what this will do is it's going to run this command with a timeout of 5 seconds. So after 5 seconds, this command is going to end, and this overall command group and add commands right here will terminate, and this autonomous routine is over. So that's pretty much it for your drive forward auto. Now, I want you to take a second and make an drive backward auto. So very similar, just make a drive backwards auto. Okay, cool. Hopefully you've done that. So let's go to command new drive backward auto, and hopefully realize you don't need any of this actually. I'm just gonna get rid of this comment. We're going to pass drive subsystem drive subsystem add commands. Oop, not that. Oops, sorry. Don't forget, extend your sequential command group. That's very important. Now we can do our add commands, and we can add new auto drive. And we're just going to pass it a negative velocity percent output, and obviously 0. There's your drive backward, and we're just going to do a timeout. Doesn't matter what it is. 5 seconds is good. And that's pretty much it. And one more thing to notice, you actually don't need a semicolon here because commands are separated by commas actually. So no need for a semicolon within your add commands. Just make sure you don't have a comma in the final statement unless it's the only statement, of course, in which case you don't need a comma. All right, so hopefully that makes some sense. So now what I want to do is run the intake while I'm driving the robot. Now, I'll tell you now, running the intake, it's very similar to your drive you're creating an autonomous range drive, you just create a new auto intake command with an add commands. It's very similar. They work the same way. It's fairly intuitive. Now, here's the tricky part. So far, we've only worked with something called a sequential command group, right? So that's basically running commands one at a time. So how exactly do we get two things on a robot to run at once, right? Because obviously we're not going to drive and then intake balls. I mean, that doesn't make sense. We want to be able to speed things up and just drive while we're intaking balls. That's the whole point of our autonomous routine that we want to lead up to. So the way we do that is with something called a parallel command group. Now, a parallel command group, as the name implies, is commands running in parallel, meaning they're running together at the same time. And thankfully, this is a part of our sequential command group, so we can do exactly that. So we're going to do the same thing always. We're going to make a new. And actually, you can make a new sequential command group here, by the way, if you want to make it easier on yourself. You didn't have to go through what I did. But for now, we're going to make it a new sequential command group. And we're going to call this drive and intake auto. And there we go. So see here, this makes it a lot easier and a lot cleaner for you to work with instead of having to delete all those commands. So in this case, where the subsystem we're going to work with, drive subsystem, drive underscore subsystem. Whoops, my spelling is bad. And then we're going to have intake subsystem. Let's call it intake. So because this is a sequential command group, we need to create a new parallel command group. So to do that, you literally just type new parallel command group. There you go. There's your new parallel command group. And what commands do you want to run in parallel? Well, we want to drive and we want to intake. So it's exactly what we're going to do. So new auto drive. We're going to pass in drive subsystem. And let's just keep things basic and move forward for now. So no rotation. At the same time, we're going to have a new auto intake. And we're going to pass an intake. And we need a speed. So let's specify a speed. Let's say I want to move it pretty slow, so 0.5 is good enough because the robot's already moving pretty fast. So there we have it. Now, one thing to keep in mind is that this entire command group is going to run forever, obviously, right? So if you want this parallel command group to end, we can actually just add a timeout on the parallel command group itself. And so that means both of these commands at the same time will stop after 5 seconds. So there you have it. There's is your drive and intake auto. So let's just recap real quick. So we have a parallel command group that's running both the drive and the intake with a timeout for 5 seconds. Now, one thing I want to keep in mind is that when you create your autonomous routines, make sure you only extend sequential command group, because as you get into more complex autonomous routines, you'll find that you're going to have multiple parallel command groups inside multiple sequential command groups. And so one thing you want to keep in mind is that your overall command is actually running sequentially and not accidentally in parallel, because then you'll have all kinds of problems with all different subsystems running at once, which we do not want. So we usually just keep it as a sequential command group and then add our own parallel command groups as necessary. So you could have made this a parallel command group, but I caution against doing that for now, because as we get more and more complex, it's going to help to keep this a sequential command group. So yeah, that's pretty much it. Now, one thing I want you guys to sort of explore with is the auto drive command. So I want you guys to see, or I want you guys to try rather, or as a challenge, to see if you can make a turn 90 auto. And basically what I want you to do is see if you can time out an autonomous command that makes the robot turn 90 degrees. So you're going to have some level of rotation here. So give that a try, and then feel free to test it on the robot and see what your results are. And as always, continue to modify and continue to iterate, and you'll get it. All right. Hope you enjoyed the video. Catch you later.